I want to go over the definition on page 124 in the textbook, and this is excuse me, the idea of representing the representation of a vector in terms of a given basis. So let me just start off with a relatively simple example. I could not have drawn that in the worst place. I'm going to erase this. That's right in the middle of the glare there. So let's talk about R2 and see what this means. Sorry about all the squeaky noise. So one of these days I'm going to get some new markers. The standard basis we could use, but I want to use something different than the standard basis to make a point of what this definition says. So let's just take, and I'm picking these vectors relatively randomly, but I want them to be fairly nice, nothing too crazy. Let's suppose this right here, this is the vector 4, 1. And let's suppose this is the vector right here, 1, let's say 3. The fact there's a 1 there and a 1 there, it's always a balance between picking something which is easy but not too easy, so that you don't want to mistakenly think there are patterns that don't exist. I want to use those two vectors as a basis. So we might even say something like this. We might say, sometimes we use a funny little b like that, a script b, but the basis here is these two vectors. So the vector 4, 1 and the vector 1, 3. Now remember, the idea with a basis is that these two vectors span the entire vector space, which is R2. So we're thinking of the vector space as R2, the plane, which is all the vectors in the plane under vector addition and scalar multiplication. Is it obvious these two vectors span it? Yeah, for all the things that we've said, because what does it mean span it? You take linear combinations of these two vectors, which means if you have any vector in the plane, we can find a linear combination of these two equal to it. Well, I actually want to do that right now. That's what I want to do. So I want to take some, well, now I could take a generic vector, A, B, or I could take a specific one. Let me take a specific one. And if I take a random specific vector, the numbers might not be very nice. So I'm not sure how random I should really make this whole thing, but I will. How about if I take some vector out here, and let's just say this is the vector 5, 9. 5, 9. This is a random choice, only it's not random. I mean, look, I used whole numbers, 5 and 9. I don't want to use anything too crazy. What I want to do is I want to represent this vector as a linear combination of these two basis vectors. What has to happen for that to be true? We have to have the following. Some multiple of this vector. Now let me write it vertically because I think it's easier when we do it this way. And this vector, 1, 3. So this equals this vector, 5, 9. The A and the B, we're going to call the coordinates of this vector relative to this basis. Because after all, if I chose two different vectors, I wouldn't get the same A and B. Hey, by the way, if I can't do this, then this is not a basis. The only way for this to be a basis is if I can do this. Now, this sets up a system of equations, right? So let's go ahead and do it. So 4A plus, 4A plus B equals 5, and A plus 3B equals 9. I guess, I don't know, Gaussian elimination. So let's, it's funny, I never feel like doing this, but at any rate, hey, look, I don't even have room here, but let's say this right here, quick. How about if I multiply that equation by 1/4? Let's do that, 1/4 and 5/4. And now that's fine, right? And then we'll take this row and we'll subtract this row, and that will give us A plus B I hope this is on screen. It looks like it when I'm like a plus, sorry, darn it all, a plus 1/4 b equals 5/4. And this minus this, the a's will be gone. This minus this, what's 3 minus 1/4? 11/4? 11/4 b equals, and then 9 minus 5/4. 9 minus 5/4, 31/4. Now, these numbers aren't bad, but this, a minute ago I said, almost no matter what I choose, we're going to run into this kind of thing here. And right away, that tells me that b is what? 31/11. That's not the end of the world. Okay, it's not the nicest number, but whatever. There's b. Now I can find a from this one right here. So this would tell me that a plus 1/4 times this, so that's 31/44, equals 5/4. And so a has to equal, let's subtract this. So 5/4 minus 31/44. Let's see, calm down, minus 44. That's 55 minus 31. And that's 14/44, I think. Hope I got that right? So let's see, 11. Coming down, minus 44. Multiply this time by 11. 55. What's 55? No, I didn't do that right. Whoa. What's 55 minus 31? Well, let's see. 55 minus 30. Oh my gosh. Scratch that. What's 55 minus 31? 24. Oh, where are all of you when I need you, right? So that's a equals 24/44. Is that right? Jeez, I don't want to mess it up here at this point. What's 55? Can you imagine the whole thing revolves on doing this? I never do this, but I can't resist right now. Just out of comedy sense, there are 4 and 2, 24. Yeah, that's not how I do it in my head. I don't think it's how you do it in your head either. But 24/44. 4 goes in there, what? 6/11. So that's 6/11. So 6/11. Now, that was kind of a lot of algebra to get the a and the b here. Now, how do we write all this down? Here's how we write it. We say that the representation of this vector with this basis is equal to this a and this b. And we're going to write it, well, we could write it in a couple of different ways. But let's write it like this. Because I think this is how the book does it. We'll write it like this. What was the a? I lost track of it. 6/11. And what was the b? 35/11. Sorry. 35/11. Now, we could have written this. This is going to go into the glare here, but I guess I could have written it like this. 6/11, comma, 35/11. And again, these are the coordinates. These are the coordinates of this vector given this basis. Now, this is the end of the video, but one thing to say before I turn this off or shut this down. If we use the standard basis for R2, if we use the standard basis for R2, what is the standard basis? That's E1, E2, or I hat, J hat. That would be this. That would be this vector, 1, 0, and 0, 1. And then where do those wind up down here? They wind up here, 1, 0, 0, 1. Well then, just look at this. You can read it right off. A plus 0 equals 5. So A would equal 5, and B would equal 9. In other words, if we use the standard basis, the coordinates of this vector are the coordinates of this vector. And that's where we get the term coordinates from. So the coordinates of a vector, frankly, in Rn, are its coordinates if the basis is the standard basis. But we could use a different basis. Maybe you remember from Calc 3, you had the TNB framework. You can get different coordinate systems. And you do a lot of times, and especially, say, in relativity in physics, you want to get a different coordinate system. for reasons that we won't go into here, but you do. And then you have to rewrite everything's position in terms of the new coordinate system, which gives you a new basis. So you get new coordinates. Man, that is abstract sounding. When I'm saying it, my head's going, really? But that's, I don't know how else to say it. I'm saying it correctly. So at any rate, the representation of this vector with this basis is this. How do you do it? You set up a linear combination equal to the vector in question and solve for these scalars, and those scalars are the coordinates of the original vector in terms of this basis. That may or may not have made things better. I don't know. More to follow.